In this video, we'll be continuing our look at the SN1 mechanism, focusing on the different factors that affect the rate of the SN1 reaction. Just as we did with SN2 reactions, let's look at steric effects on SN1 reactions. So if we have an alkyl halide and we treat it with formic acid to give this substitution product, we are only providing a very weak nucleophile, and so this pretty much ensures that the reaction has to proceed through the SN1 mechanism. SN2 requires a stronger nucleophile. Here we have a methyl, primary, secondary, and tertiary alkyl halide. And again, these conditions don't allow SN2, it's really forcing SN1. And the relative rate, if we call this, if we call the primary 1, the methyl bromide is 0.6, and then the secondary alkyl halide reacts 26 times faster, and then the tertiary alkyl halide reacts 100 million times faster. So for SN1 reactions, tertiary alkyl halides react much faster than secondary, which react much faster than primary, which are much faster than methyl. So primary and methyl alkyl halides are normally not going to undergo SN1 reactions. This was a way just to force it to happen, really just to demonstrate that this reaction is really bad. But as we see the relative rate of the reaction, this makes sense because if we think about carbocation stability, a tertiary carbocation is more stable than a secondary carbocation. And so the tertiary carbocation will be lower energy than a secondary carbocation. The transition state leading to the tertiary will be lower than the transition state leading to the secondary. So the activation energy for the formation of a tertiary carbocation will be smaller than the activation energy leading to a secondary carbocation. And that's what we see here in terms of the relative rate. A big difference in activation energy leading to a big difference in the rate of the reaction. Next, let's take a look at nucleophile effects. So if we have T-butyl bromide and we treat this with water, we are going to form T-butyl alcohol. If we add more water, well, that's not going to have any effect on the reaction. Because remember, for an SN1 reaction, the rate is equal to the rate constant K times the concentration of the alkyl halide. So the nucleophile does not appear in the rate law. Changing the concentration of water doesn't affect the rate. If we used a stronger nucleophile, instead of water, if we used hydroxide, well, this is not going to make an SN1 reaction happen faster. Instead, it's going to do other reactions. So this is not going to have an impact on the SN1 reaction. All right, let's look at just one more example because I want to prove to you that the nucleophile doesn't matter. So here we have T-butyl chloride, T-butyl chloride. We can react this with methanol to give this ether, or we can react it with water to give this alcohol. And in terms of relative rate, if we call this 1, then with water, this has a relative rate of 37,500. So this is a problem because the rate is equal to the rate constant K times the concentration of the alkyl halide. The nucleophile does not appear in the rate law, but we see that methanol versus water greatly affects the rate of the reaction. Well, for a solvolysis reaction, the nucleophile is the solvent. So technically, the nucleophile doesn't affect the rate of the reaction. The solvent is what affects the rate of the reaction. So the nucleophile does not appear in the rate law, but we do have to take into consideration then not nucleophile effects, but solvent effects. So we just saw for the same substrate solvolysis reactions If we use methanol, this is a slower reaction. And if we use water, this is a faster reaction. Well, we need to focus on something called the dielectric constant, which is given the Greek symbol epsilon, and it is the ability to moderate plus minus attraction. So as the dielectric constant increases, the ability to solvate cations and anions increases. So for methanol, this has a dielectric constant of 33. Water has a dielectric constant of 78. So water has a much higher dielectric constant. It is better able to moderate the attraction between positive and negative. For example, if we have no solvent present, then our cation would be right next to our anion. If we have a solvent with kind of a medium dielectric constant, then our positive and negative will be separated because we're going to have these solvent molecules around. But if we have a solvent with a very high dielectric constant, this cation is going to be way far away from the anion, and it will be solvated by lots of molecules. So what do we care about cations and anions in this reaction? Well, think about our starting material is T-butyl chloride. And because of the difference in electronegativity between chlorine and carbon, chlorine will have a small partial negative, and this carbon will have a small partial positive. And then our intermediate is the carbocation and the chloride. And our transition state looks like this. Now, because the chlorine is pulling away electrons, we now have a bigger partial negative on the chlorine and a bigger partial positive on this carbon. And if we're pretending there's no solvent, this would be our activation energy. As we think about solvent effects, we're going to speed up the reaction if we can decrease the activation energy. If we increase the energy of the starting material or decrease the energy of the transition state, that's going to speed things up. If we increase the energy of the transition state without affecting the starting material, that's going to increase the activation energy and slow the reaction down. So you need to think about whether a solvent can stabilize the starting material, the product, or the transition state. All of them, none of them, to what extent? So if we have a solvent with a large dielectric constant, what can that do? Because we have a little bit of charge here, a solvent with a high dielectric constant can stabilize it just a little bit. So maybe this is going to be a teeny bit lower. If we think about our carbocation intermediate, these will definitely be solvated and stabilized by a solvent with a high dielectric constant. So this one is going to be stabilized a lot, much lower energy. But actually, we don't care about that as much as we care about the transition state. Here, because we have a bigger partial positive, a bigger partial negative compared to what we had here, a solvent with a high dielectric constant is going to be more effective at stabilizing this species. And so maybe this is going to be stabilized this much, right? So instead of being at this energy, it'll be stabilized down to this energy. So now this reaction looks like this, and here is our new activation energy. So the starting material was stabilized just a little bit, but the transition state was stabilized significantly. And so overall, that leads to a smaller activation energy, which means the reaction will be faster. So the better the solvent is at stabilizing charge, the faster this reaction can proceed. Right, so anytime you can stabilize the transition state more than you stabilize the starting material, you are going to decrease the activation energy, which increases the rate of the reaction. So in terms of solvent effects on SN1 reactions, the faster reaction will involve the solvent with the higher dielectric constant. So to summarize the SN1 reaction, we know that this will work with tertiary alkyl halides or other substrates. It will work with some secondary as well, but it will not work with primary or methyl. Remember, for secondary alkyl halides or other substrates, if you have a moderate nucleophile, it can do SN2. If you have a very, very weak nucleophile, then it can do SN1. The rate law for an SN1 reaction tells us that the rate is equal to a rate constant K times the concentration of the substrate, not the nucleophile. SN1 because it is unimolecular, only one molecule in the transition state of the rate determining step. The mechanism proceeds by carbocation formation, followed by nucleophilic attack. For substrates that have a chirality center, the SN1 mechanism leads to partial racemization with an excess of inversion. How much inversion depends on how stable or unstable the carbocation. Steric effects, the more substituted, the faster. And so the overall rate of the reaction follows the stability of carbocations. Now, we've talked about tertiary compared to secondary, compared to primary, compared to methyl, but also long, long ago, we reviewed resonance. So you may come across some carbocations that could be further stabilized by resonance. So for example, if you have, let's say we have this and bromine leaves and we get a carbocation, well, wait a minute, this looks like a primary carbocation, but we can draw another resonance structure. If we imagine these electrons move here, then we get another resonance structure that looks like this. And so you'll want to be on the lookout for other types of carbocations that can be stabilized by resonance, as well as being stabilized by hyperconjugation and inductive effect. For the SN1 reaction, the nucleophile doesn't have an effect as a nucleophile, but it can have an effect if it is the solvent. And so solvent effects, a polar solvent is preferred. The higher the dielectric constant, the faster the reaction will be.